One of the risks of threading is the emergence of properties that we don't like, things which are caused by threading and things happening either at the same time or alongside each other that lead to emergent properties. And one of the most common things we will see is called a race condition. So a race condition in programming is, in this context, where threads are attempting to update the same variable, the same item memory, perform an operation, and because they are happening at the same time in parallel to each other, that operation gets messed up, something goes wrong, and we have an uncertain outcome. So we've created a little bit of a contrived example here to demonstrate hopefully a race condition. So we've gone in, we have our counter variable, we then begin a parallel region, we put the counter into a temporary counter. Now that's a temporary counter within the parallel region, so that's a temporary counter within the thread. We then say hello from thread number, and my TC, my temporary counter, is this, gives the value. We then increment the temporary counter, and then we set the counter back to be that temporary counter value. Now if we compile this, in fact if we ran this as a single threaded thing, we would get the increment, TC would increment, it would be read back to counter, and it would happen the number of times that this was executed. So in this parallel environment, this is going to execute 10 times, there's going to be 10 threads. So what should happen is temporary counter gets incremented 10 times and therefore counter set to it. So we would expect counter to come out 0 plus 10 or 10 out the end. Let's have a look at what actually happens. And you can see that we've gone through, and in each thread temporary counter is 0 because it's started and it's read in TC, which is 0 as the thread starts. Let's at the end here printf and put the final counter variable, which again we're expecting to be 10. And you can see the final counter is 2, is 1, is 1. And we will get slightly inconsistent results. Now, if we don't print this out, i.e. if we include no delay within it, then fairly commonly now we will get 10 as the output. Why? Because this execution takes so little time that each thread starts, goes through and executes it. So it's 0, adds 1 to it, sets counter to 1. It's finished before the next thread starts. The next thread then gets 1, 2, sets it to 2, next thread, and so on. But, and this is why race conditions are dangerous, it doesn't always happen. So we've created this contrived environment here where most of the time we don't see anything. So if we were running an integration test, pass, 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 we run it 3 times, it passes, we then find that occasionally we get a bad answer. By putting this in, what we're doing is we're delaying the execution of this thread long enough that the other threads start, get it as 0, and then what happens is we are able to more clearly see the error rather than it being more hidden. So threads are very dangerous. If we are updating shared items of memory, if we're updating shared variables, we need to think very carefully in the order in which things happen, and we need to try and keep these safe. Now this is quite a complicated task and there's a lot of ways in which we can do this. Later on we will start looking at inbuilt methods to handle updates and handle increments and these kind of things, and there's some very clever things built into OpenMP and some good ways we can start thinking about it. But what we'll just quickly introduce is the idea of the critical section. So a critical section in OpenMP is an area that can only be entered by one thread at a time. So if we now come back to here, oops. and wrap this in a critical section. Here's our parallel region, but we're putting this into a critical section, which means that only one thread can enter it at a time. And now we are getting the expected result. We have made this safe because the reading from the variable, the update to the internal variable, and then importantly the update to the global variable all happen in the critical sections. Only one thread can enter this at once. Now, of course, you would look at this and say, well, you've just undone parallel. You've created a parallel team, you've gone to the overhead of doing that, and then you've said only one at a time can go in and execute this code. And you're absolutely correct. But we're just demonstrating an approach to allow safety within parallelism to avoid the race condition that we're going to see. We put this back out. And we're back to having an example of how dangerous these conditions can be. Later on, we will come to look at the myriad of other options to do with updating this, but it is important to always remember that there is an inherent danger when we are side effecting, when we are updating things outside of the thread itself. There is a natural danger to overlook what happens when multiple updates happen at the same time. Risk of race conditions, and if you read up on race conditions, you'll find that they have led to a number of very, very serious and deadly software faults.